delighted to be here. I don't know whether this is an exercise on, this late in the day on Friday afternoon, my ability to entertain you or your ability to withstand boring facts, but we'll press on here. So I think Chuck did a good job. I've worked for the Army, protecting tactical systems. That's where I started against EMP. Then I transitioned into the Defense Nuclear Agency, looking more at strategic systems and developing standards. And then finally, with the Defense Threat Reduction Agency, I was the director of their hardened target research facility. And then I left there and went, I just retired from James Madison University. I was professor of applied science there. So I feel like I've been through the gamut, and but hopefully what my experience will be of some value to the quest here. What I want to do today, first and foremost, just the agency that has the most experience, or the department that has had the most experience with EMP protection is the Department of Defense, and we all stand to learn a lot from their experience, their hard-learned lessons, and so most of what I want to say today, and I'll try to speed it up, maybe save us some time, is based upon my experience developing EMP protection techniques and standards at the Department of Defense. So if I can figure out how to use this, this is an IQ test, I can tell. All right, so I want to start with some quotes that I think are particularly appropriate when we think about EMP and what's been done and what hasn't been done. I'm a UVA graduate, so I have to have the obligatory Thomas Jefferson quote, we're not afraid to pursue the truth no matter where the search may lead. I think this is a very important adage vis-a-vis EMP and GMD effects. And then this Henry Kissinger quote, so I've got a liberal and a conservative here. I like the Kissinger quote, and this is what's happening. We're avoiding coming to grips with problems by making projections of probable events which require little action. That's what's happening. We are making assumptions about the course of history that are serving as a substitute for effort. That is happening. And we need to remember, especially the policymaker, policy level, need to remember that they're responsible not only for the best thing that could happen, the best case scenario, but also for the worst. And that we can't entrust the survival of our society entirely to guesses. And I'm sorry to say that's what's happening. So there's a lot of work to be done. We need to get with it, and hopefully what I have to tell you based on the DoD experience will help. Okay. So here's the basic plan of attack here. Emphasis on lessons from the DoD experience. Okay. So first, just some ways to think about cost. I hear a lot of people talking about cost, but there's some very, very, very simple ways to think about cost. And when we talk about these high incident, low frequency HILF type effects, which EMP is one, actually a better acronym is high effect, low likelihood. These are HEL effects. Okay. So the cost for this kind of protection is offset by normally unobserved benefits. If you don't have an EMP, you can't tell. It's like snapping your fingers to keep the elephants away, right? Anytime I talk to somebody about EMP, the first thing I have to do is do an existence proof, credulity proof, and that gets to be very old. And I think that's changing, but I hope it is. The probability of people say, well, this is never going to happen, and if it were, there's no way I can predict the probability. Well, that's wrong. There's a guy named Martin Hellman, who Beta Tau, the IEEE Mensa Society, who has done very elaborate predictions of the probability of nuclear attacks, and he has bounded the probabilities, and they're very high, that we will have a nuclear weapon detonated, okay, in an unfriendly manner. So I Google Martin Hellman. The other thing is EMP protection is not highly visible, and when it works, It's often taken for granted by management and customers. And we find in DoD it's very easy to forgo, because of this lack of visibility, easy to forgo maintenance of EMP protection. Corporations make their money by selling products and services, but protective security with which they operate is often an afterthought at best, and these hill for hell type effects are the lowest of the low in terms of the afterthoughts. Okay. But the problem is, and this is where we're going to go into this very simple cost modeling, is that neglect of EMP protection has very serious financial, even existential consequences. So obviously, we need to remember that businesses know more about themselves and their systems than we do, and that they know about also they know more than they know about potential threats, and that's where we need to educate, create awareness. The benefit of protection systems is not easy to characterize, but it can be done, and I'll try to show you how here. We need to treat the problem by considering losses and using combinations of failure probabilities and associated consequences. And the basic idea is more protection means lower risk of losses. I mean, businesses understand losses, so we want to do the cost arguments in terms of lowering the risk of losses. The other thing is, we have to remember that perfect protection is not possible. We need to recognize that. You're never going to have a perfectly survivable system, so quit trying, okay? And that was a message that came through pretty loud and clear in several other presentations today. But we have to begin our thinking about cost here. So we have a line here. Does this come off the? Yeah. Okay. Pull hard. So here's a line, and it's a line of increasing protection till you get to the point of perfect protection, but you're never going to get there. And then in the opposite direction is the direction of increasing risk. So the less the protection, the bigger the risk, okay? Basic idea, understand? So we can draw a protection cost profile. And the smaller the amount of protection, the smaller the cost, and the cost will go up in some asymptotic way. You're never going to get to this perfect protection point here. So you can waste a lot of money on protection. We want to avoid that, okay? But this line is not adequate. The protection profile doesn't allow determining the optimum protection level. And that's the basic message of that chart. So there's another line we can draw, and that's the loss profile. And if we don't protect, the costs can be very, very high. In fact, we're talking, this Lloyd's of London report was talking in the terms of trillions, single-digit trillions of dollars if we would to suffer a major grid collapse. And now, if we're thinking about communication systems like FirstNet, you're going to need that communication system to restore the grid. So the cost of not having the communication, the ground awareness that you get from a communication system, I think also you could put the costs up, in the trillions of dollars for not being able to restore the grid in a timely fashion. So both the communication, losing the communication system, and the grid communication engender similar costs. So if we increase the protection, it brings down the cost. Of course, you never will get to perfect protection here. This is the value of the losses as we increase the protection. All right. So the bottom line, the greater the potential EMP damages, the bigger the benefit of preventing it. And as I say, for long-term outages, you're talking about things that are on the scale of gross national products. Okay. So if we superimpose these charts, then we start to get an idea that there might be some optimum cost where the amount of money we've invested in the protection equals the amount of losses that we prevented. And any costs we incur that are beyond this point are probably wasted. Okay. So you have this point E where the protection expenditures are justified. And to the left of E, there's probably some benefit I mean, if you can keep the costs down here, it's even better, but here's the optimum cost. We have to have some idea of how much the losses are so we have some basis for justifying our investment. Now, if you look at the real situation for an EMP, the protection profile, the cost of protection is really low compared to the value of the losses. I mean, you know, I wish I had I could have plotted this in a log plot, but the protection costs are very low. In fact, they're so low that you probably can get pretty close to a really effective, not perfect, but a very effective protection for an investment that would be very low. Okay. All right. So that's the basic way of thinking about costs. It's very, you know, very simple, but I think it helps us as we go forward. Okay. So now, what I want to do, again, based upon the DoD experience, to gain insights into the risk and protection, you know, that interplay on the horizontal axis, let's look at the evolution of EMP protection philosophy within the Department of Defense. Okay, I'm not even, okay, so in the Department of Defense, we had a very, very intense debate from the early 1960s to the early 1980s, and it was so intense that there were people who lost their jobs because of the conflict between these two. Okay, and the basic conflict was caused by, you have this tailored hardening approach where you're protecting at the box level. You go into a data center and you say, I think this box might be vulnerable because it's sitting over here near the door, and these boxes might not be vulnerable. This other box, since it's where the power line comes in, that might be vulnerable. And so you're doing a box level protection. This was done, there's some places in Washington here where this was done. It was almost like people were hanging surge arresters on lines sort of randomly. But he had much lower initial cost, but it was based on a lot of guesswork. Okay. Then you had people who thought, no, you just need to put all of your electronics inside a shield. It's going to cost more, but procedures. Unfortunately, we have people who think you can harden systems by just developing workaround procedures. Here in the DoD, we never thought about that because we were protecting systems that were time urgent. Well, you know, the systems that had to be able to respond to a missile attack where you only had 30 minutes of warning. Now, think about the power grid problem. How much warning are we going to get for the solar storm hitting the power grid? Anybody remember?
20 minutes.
About 30 minutes. So the amount of warning that we're going to have for the power grid is about exactly the same as the amount of warning we get from a missile attack. So we're not going to have time to do operational procedures. That's another reason not to do operational procedures. Now, this debate, as I say, there were people who lost their jobs because of the conflict over these. But the debate precipitated two high-level reviews, one by the Defense Science Board, the other by the National Academy of Sciences. And this point, I'm not going to dwell on this, but EMP, we know that it's very difficult to predict EMP effects. And I'm not going to dwell on this. It's going to take a little too much time to explain. But the idea is you can predict the currents and voltages outside a system, but as you go down inside the system, it's very, very difficult to predict what kind of currents and voltages you would have at individual components. Okay, and this is where the tailored hardening was trying to protect. Okay, so that's really the crux of the issue. So what you do is you keep the energy out of the system, and then you don't have to worry about predicting what happens down here. Okay, that's the idea. You put up a shield barrier. So the National Research Council of the National Academy of Sciences said that they were very concerned about prediction uncertainty, as I mentioned, and they said the soundest results can be attained where the stress within the system is controlled through integral shielding. That was the National Academy of Sciences. And be great emphasis on developing better and cheaper means for virtually complete and effective shielding of systems. Okay, that was the idea. They also said that we need to develop design strategies that were testable, and if the system is shielded so well that nothing gets through the, or virtually nothing gets past the shield, it makes the testing much easier. And then on tailored hardening, they said that this carries much more risk of vulnerability doing the tailored hardening approach, the component level protection rather than the system level. And there's again, they pointed to the inaccuracy of the analytical predictions. Right, then the Defense Science Board came to the same conclusions. Tailored design, too much analysis, hardening components. The component level is very difficult. Best approach is a minimum number of contiguous shields. Okay, so these two groups came to virtually the same conclusions. So the DoD has used this system-level global shielding approach, and the idea is to make things that are electromagnetically simple. We know how to do that. The engineering is very straightforward. Also, you need to be able to maintain the hardness. If you're going to harden the system and not maintain it and surveil it, it's like throwing your money out the window. Okay? And here are some systems that the DoD. This is not all-inclusive, but the systems that we have effectively hardened using the global shielding approach. And we actually developed a military standard back in around, well, it was completed in 1990, and we were able to get Army, Navy, a tri-service group together. And the major issue, we were still talking about boxer system level, but we resolved standard requires protection at the system level and applies to all systems, DoD systems. And it specifies protection measures, not vendors. I talk to people, I say we need standards for protecting the power grid. They say no, all you're trying to do is just get your vendor buddies funded. But the standards, if properly written, say nothing about vendors, and neither, the DoD standards say nothing. They just have the protection measures, the decibels of shielding, the voltage residual levels and current residual levels inside that shield. You can do it however you want, as long as when we test it, that the voltages are limited. Here's just a notional schematic of how you do it. And so you have the shield barrier, and every penetration is protected. Every conducting penetration and breach type penetration, the doors and the pipes is protected. And so you have a quiet zone inside here, and you can put anything you want inside here. You can put commercial off-the-shelf systems. You can put any kind of electronics, because inside the shield is very electromagnetically very quiet. Okay, that's the idea. And I should mention, I don't show it in here, but these neutral blocking devices are exactly the same idea as a barrier. You put that capacitor blocking device, you can put anything you want on the other side of it, and it also takes away all the uncertainty of what's the highest field you can, or GMD current. You can have GMD currents that vary over a factor of 1,000, and it's good. It doesn't matter. A capacitor is going to block it. And the same way on the receiving end, you don't have to test all the transformers, because if there's no DC current coming through, it doesn't matter what you put on the other side of that capacitor. Okay. So here's a picture of the Defense Satellite Communication System ground terminals. We hardened those using the MIL standard 188-125. And there's some ways to reduce cost. You don't have to shield entire buildings. You can isolate your critical electronics inside shielded rooms. There are lots of people who build these. Or you can put them inside, in some cases, you can just put them inside shielded cabinets that you install with fiber optic interconnects. Other thing I should mention, Brian Chakotis is doing a lot of good work on looking at different ways of dielectrically isolating electronics from the outside world, and I encourage you to talk to him about his results. So I think, is there anything anymore? Okay, just by way of summary, protection costs are well justified if you looked at the cost of the consequences. The costs are a small fraction of system costs for new systems. Our experience in DoD is 2 to 5% of the nukes if you get come in at the beginning. They're manageable for protection of existing systems, especially if you can isolate the critical electronics. EMP protection has a lot of other benefits in terms of protection against electric power outages, lightning, general power line transients, GMD, electromagnetic interference, signal emanation security, called Tempest, and RF weapons effect. The EMP protection helps you in a lot of other ways. And I have to emphasize the importance of protecting the backup power. That has to be integral to your approach. So and we've done this. The Department of Defense has hardened, I think it's fair to say, hundreds of systems using this approach. So it's a doable do. That's all I have.
Thank you very much, George. So, if you work in the data center world, which we'll be talking about in a little while, there are a lot of people who spend a lot of money just trying to keep equipment protected from what they would call dirty power and things like that, which degrades systems and costs money. So what I'd like to do is have some questions in a moment, but before we do, I'd like to have David Oppenheimer come from Pathion, maybe say a sentence or two about yourself, and get us interested in what's coming down the pike a little bit in solid-state storage of energy.
Thank you for having me here, Chuck. I appreciate the opportunity. I've worked with Paul Rich and his group here at the PSO over the last few years and always enjoy coming out. I'm with Pathion Incorporated. We are an energy company based out of Los Gatos, California as a headquarters. And fundamentally, what we are is a technology company, material sciences. Those sciences came out of groups like Los Alamos National Labs and Berkeley National Labs. What has happened in the energy technology and particularly storage of energy in the last 10 years is a revolution on the basis that how batteries go together has changed. We're familiar with the physics of traditional batteries, a little chemistry here, a little chemistry there. The answer is a little of that's not quite so correct anymore. And that revolution in knowledge is going to cause a generation in batteries that will be significantly better than the kind we have today. That being said, what is the use of a battery in this solution set? How do we make microgrids that make sense? And some of this is just plain strategy issues. Let's say this building has multiple power sources. It has solar, it has natural gas, it has generators, and it has power coming in from outside sources. Well, one of the best techniques you can do is take all of that power and pump it through your batteries. Why? Because all of the issues that we've been talking about here don't pass through those batteries. The batteries give the building clean, even, uninterruptible power. Now let's go a little bit further. We have peak usage periods that have dogged this country, frankly, for a long, long time. We all get the bill, don't we? That smart meter, that's not our friend, is it? So we know that we're paying for peak power at a real premium. What if this microgrid was under the control partially of the local utility? And so I could shift the building purely off the grid, 3-4 hours a day at the right time. Suddenly I even out my power usage around the country. There's a real economic value to there, isn't that? I mean, that actually changes a proposition here. What we have to do to make this solution work to avoid EMP vulnerability is upgrade this network in a way that takes care of that and creates financial value to do it. What we're offering forward is the capacity to have batteries that are deep cycle, that can take a building onto it and take it off the grid. And whether that is in a pulsed manner, so that the building is on for 10 minutes and off for 10 minutes, or on for a day and off for a day, those are all strategy issues of how you deploy the technology. But fundamentally, you can isolate a building. And by doing that, you provide clean power, you provide a barrier for EMP, and you create economic value by removing peak usage periods. You even those out across large areas. That's an alternative to how microgrids might be viewed in the future. When I was in nuclear non-proliferation, we were reminded that there were 3 things that you always had to do. First was tell somebody they have a problem. Once you got a consensus that they understood that they had a problem, you went on to a technology that could solve that problem. And then lastly, you had to find a way to finance that solution. And that's the kicker most of the time. And so the answer here is, if you can't find actual economic value in improving the network to do this, it's going to be a very difficult measure. But I believe there is economic value in upgrading the network this way. And it's not about the utility owners, it's about the power users. Thank you, and I appreciate my opportunity to speak. Chuck?
Thank you. I had a quick question myself for you. Sounds like a great set of strategies. You have a sense of where we are today with the cost of, say, energy storage. Let's say all the energy storage in the country was costing us $1. With your new technology that you're seeing, some of yours, some of others, a few years down the road, what will that new technology do to that cost? If all energy storage today cost $1, how much will that same amount of energy storage cost when we realize the benefits of these new technologies?
Well, I think that the question is a transition from one modality to another modality. Batteries have a cost, and that cost is never going to go to 0. But because they're going to have much, much longer life and be able to perform effectively over a great deal longer time and in depth, they can provide better energy output, they can provide better power output. There's a difference between power and energy batteries. That cost is simply neutralized or managed by the savings that you have, similar to solar systems.
So it's going to get better?
It's going to get better.
By a teeny-weeny little bit or by a meaningful amount?
Well, if we were to just look at a battery, and the battery were 50% or 100% more powerful or more effective than a current battery, then by definition it's half the price.
Wow, half the price. Wow, it sounds like we're almost there. Very good. Now, I'd like to give the audience a chance for a question or two to either Dr. Baker or, okay, and identify yourself, please. You seem like a stranger.
I'm Bill Joyce with AFS. I'm in the dark ages on batteries, but I know when I try to charge a battery, if I put too many amps through, you know, the battery's toast. These batteries right now can take this square wave EMP pulse coming through with all that energy and they're unaffected, unlike solid state devices?
Well, as larger systems, a system deployment, you would be able to protect against that in the way that's been described by this group. So you would have filters in the front end, and you would take the power into the batteries, and yes, they're much more resilient than the systems that would normally be taking that power directly.
Okay, so what you're saying is there's a system in front of the battery to screen out EMP.
That's correct.
Great question. Thank you, Dr. Joyce. I see a question here, and then back to you.
This is Brian Chakotis. I'm aware that West Virginia, in some cases, is using battery banks to take care of their peak power loads, capacity requirements, rather than building new power line capacity to bring in the power from somewhere else. Do you know, can you tell us a little bit about that? The other thing is, if you look at, for example, the Nissan Leaf battery, that battery has a capacity of about 20 kilowatt hours. Its cost is somewhere in the area of $11,000. And they're now configuring those batteries not for the car use only, but for whatever use you may want to put it to.
Being a West Coaster, we hear nothing of Virginia's projects, I'm afraid. So I can't comment as to how they're doing that, but that does speak to the issue of evening out the cost of the peak. The peak is so significant that even at that cost model, you're saving money fairly quickly. Now, when it comes to the larger cells and the cost per cell, it is a case-by-case basis of how you deploy it. And I really can't comment directly to that.
All right, two more quick questions, one here, and then moving to the front. Identify yourself.
Paul Kanan from Georgetown University. What is the status of legislation on providing safe power for cities if there were particularly a geomagnetic event of some sort and it knocked out power to cities? You'd be talking about millions of people in jeopardy, especially if the power couldn't be restored for months. How much good would batteries do to provide safety? And more specifically, what is the status, not so much of national defense protection, but of public health protection in terms of power vulnerability?
I'll take a stab at it. You might want to add. The status of legislation is stalled. We lost the GRID Act that was stalled, and now the SHIELD Act, I think, is following suit. And this legislation would empower FERC, the Federal Energy Regulatory Commission, to issue or to mandate standard protection of the grid. So that those, it's going to be real important to pass that or similar legislation. And there's this new, what is it, SEPA Act, which I think also would help in that regard to be able to, ensure that the grid is protected. But regarding the battery question, I'll pass the mic here.
So please restate your question on batteries.
What's the, how much will batteries help if you're without power for weeks or months? The battery supply is for days, right?
That's correct. Actually, it all has to be part of an integrated solution. That is that you need off-grid power creation. It evens out these situations so that you are not vulnerable and losing systems, but doesn't create the power. Now, it does go a lot longer than batteries that we conventionally understand today, but you still have to have an energy source in.
It could be very helpful then. The most important thing would be to coordinate rescue efforts, which would be enormous, and you'd need to have some power to provide the communications.
That's correct.
Even if there wasn't enough to heat houses and so on.
It is.
And that act he's referring to a moment ago is the act that would be a Homeland Security-oriented planning activity that looks like it has a pretty good chance of passage from what we've learned. One more question.
Well, I want to refer back to something that Bill Joyce said earlier. Oh, I'm Alan Roth with AFS. Something that Bill Joyce said earlier about our look at Mill Standard 188-125A, and we see this as weak. And George mentioned the shielding that's been studied and shown to work over many, many years that the military uses. But we have a special circumstance with our, I think, our non-nuclear EMP, our EMP generator, that has shown that the 188-125A failed, at least with this one, the testing that we did. And what I'm saying, though, is we're not saying, well, believe us or believe him, or, you know, whatever regarding shielding. We're planning to do testing, and we have really remarkable test facilities to do this, to bring on board George and others to the realities that we think are there, that they will see through our testing. And I would say just to stay tuned in to see what happens, because shielding really could be an issue that you may not see now, that would be in the future regarding this.
I think we'll give the panel or George a chance to answer that. I think, too, it's like what you're basically saying, Alan, is that we're looking at a different threat that they were looking at. They've looked at one threat, and you're trying to say, well, there's another type of threat. Georgia, do you want to comment on any of that?
You know, one point, you know, this is important. That's a very good question. The EMP standard protects systems from 1 gigahertz and below. So, okay. And the sweet spot for the RF weapon, non-nuclear weapons, spans the frequency range from 10 megahertz up to 10 gigahertz. So there is a frequency band from 1 gigahertz to 10 gigahertz where the EMP protection is not designed. Now, that's not to say there might be some inherent residual protection in that regime, but if you're worried about the RF weapons, the non-nuclear weapons, yeah, you need to be a little more fastidious with your shielding and your door seams and your wave guides.
Thank you. It almost seems like they mentioned the opposite kind of a problem. EMP issues are when an electromagnetic field is impacting you. And the opposite also happens when you are typing on your computer. In the old days, you emanate little radio signals, and smart guys in a van across the street can capture those with an antenna and then decode everything going on in your computer. And so that program was called Tempest, which is almost the opposite of EMP. You're shielding it so things don't get out. So what's interesting is to blend the combination of those problems so that you're looking at all the issues for things coming in that you don't want, as well as things going out that you don't want, right? And so harmonizing those would be very interesting, and a number of us have been talking about harmonizing all the mil specs and all the problems into sort of a harmonized standard for all of these. And we only have like conversation and emerging industry practice about that. So all of these are ongoing issues.